Guys, my name is IBM, and today I'm going to take you to lesson 7, I think. And lesson 7 will be basically about polarization, waves and superposition. Lesson 7 is going to be polarization. But before we do that, I would like to remind you of the course outline of AS Physics, where we cover physical quantities and units, errors and uncertainties, treatment of uncertainties, kinematics, dynamics, force, density, and pressure, work, energy, and power, deformation of solids, waves and superposition, electricity and DC circuits, and also particle physics. And currently, we are dealing with waves and superposition, and this is going to be lesson 7, where we shall talk about polarization. Okay, so don't forget this is AS Physics 9702, but I said it is still going to be useful to think about this as the same concepts of physics that are taught in other curricula, because AQA, I think waves still remains waves. If you're doing modeling of physics, or if you're doing physics, exploring physics, or if you're doing another curriculum which is involving physics, I'm very certain that the concepts of waves are almost the same, although the details may differ from one syllabus to another syllabus. So this is lesson 7, and I want us to start with polarization. So in lesson 6, I think in lesson 6 we were concentrating on, or we talked about electromagnetic waves and the electromagnetic spectrum, and we explored the 7 regions of the electromagnetic spectrum, which should now be concepts that we are familiar with. Okay, let's talk about polarization, and I will start with a simple analogy of polarization. So in this demonstration, or in this diagram that we see on the screen, we have a demonstration where you have a rope, and this rope can be made to move in different planes as indicated by these red arrows. But then we can make this rope to pass through maybe an opening where only vibrations in one direction can propagate to the other end, or to the fixed end of the rope. So to understand what we mean by polarization, we are going to start with a simple analogy. So imagine you fixed one end of the rope to a post as shown in this diagram, and grab the other end of the rope and pull it tight so that it is stretched out horizontally as shown in the diagram. Then move the rope repeatedly vertically up and down. So you move the rope repeatedly vertically up and down. So the vibration, this will produce a transverse wave on the rope. The vibrations of the rope are in just one plane. They will only be up and down, up and down. That is just one plane, which is going to be the vertical plane. So the vibrations are going to be described as plane polarized in the vertical plane. So it's like polarization involves ensuring that the vibrations are in one plane. So you move the rope up and down so that the rope vibrates, or the rope moves up and down, causing the vibrations to be up and down in the vertical plane. That means we shall have vibrations in just one plane, and these vibrations are going to be described as being plane polarized but in the vertical plane. You could also produce plane polarized vibrations in the horizontal plane by moving the rope horizontally, or by moving the rope repeatedly from side to side. So instead of moving the rope up and down, imagine you move the rope from side to side. So you would cause vibrations in the horizontal plane. So we say, or we would describe the vibrations as being plane polarized in the horizontal plane. So if you then now keep changing from horizontal to vertical, or vertical to horizontal, if you keep changing the direction of vibration of the rope, you will now produce an unpolarized wave where the vibrations are in more than one plane. Remember, in the first case, we moved the rope up and down, and the vibrations were only in the vertical plane. In the second case, we moved the rope side to side, which made the vibrations only to be in the horizontal. Now, if we first move in the horizontal, vertical, then followed by horizontal, followed by vertical, followed by horizontal, and the pattern continues, in other words, we are keeping changing planes, we are keeping changing directions of vibration of the rope, then we are going to produce vibrations in all planes. We are going to produce vibrations in several directions. So we shall say we have produced unpolarized vibrations of the wave. So if vibrations are in more than one plane, then they are considered to be unpolarized. But we are interested in polarization. So if if the unpolarized wave is incident at a vertical slit, for example, this one here. Now we have here vibrations in more than one plane because we said we could move the rope in several other planes in several directions, keeping changing directions so that we produce vibrations in more than one plane. And then the rope is, these vibrations are directed to a vertical slit as this one here. So the vertical slit will cut off the vibrations in several other planes and only allow vibrations in the vertical plane to go through. So what is emerging is vibrations in the vertical plane, yet we had initially vibrations in more than one plane. So if the unpolarized wave is incident at a vertical slit, then all vibrations other than those in the vertical plane, that is the ones in the blue, will be blocked. So we have here vibrations in several other planes, and these vibrations are incident onto a vertical slit. And we notice that the horizontal vibrations, which are indicated in red, are being blocked, and only the vertical vibrations, which are indicated in blue, are only passing through. But of course, I added another slit here, which was also horizontal. Because the vibrations in blue were vertical, this slit couldn't also allow them to go through. So, in the first case, the first slit has helped us to achieve what we call plane polarized waves. The waves which had vibrations in several planes before reaching the vertical slit were confined or were forced to only allow vibrations in one plane to go through. So we say the slit has carried out what we call polarizing the wave or polarizing the waves. So the waves or the wave passing through the slit will be a plane polarized wave in the vertical plane. However, if we rotated the slit or we added another slit after that, which was horizontal like this one, or when the slit is rotated through 90 degrees, the plane polarized wave will be blocked too, and no waves emerge. So if I have another slit which is now horizontal, that is, the vertical slit was vertical. I mean, the first slit was vertical and the other one is horizontal. That means this has been a rotation through an angle of 90 degrees, and therefore the vertically polarized wave will no longer pass through the horizontal slit. So we are now building the concept of polarization. The first slit has only allowed the vibrations in one plane. So polarization therefore involves confining or making vibrations of a wave to only be in one plane. So now recall that an electromagnetic wave, which we talked about earlier on, consists of an alternating magnetic field and an alternating electric field. So we saw this earlier on that an electromagnetic wave consists of an electric field vector which vibrates in one plane. For example, this keeps vibrating. Let's say it is vibrating up and down, but remember they keep alternating their planes of vibration. But in all cases, the magnetic field plane and the electric field plane will always be at right angles, but they keep alternating the planes. You may find that at one point the E is vertical and B is horizontal, and then the next case the E could be horizontal and the B is vertical. So they keep alternating their planes, but they travel or they propagate as vibrations which are perpendicular to each other, or the electric and magnetic fields are perpendicular to each other, and then they also propagate perpendicular to the direction of propagation of energy. That's why we call this to be transverse. So earlier on, we described the transverse nature of electromagnetic waves as being made up of electric and magnetic fields vibrating or oscillating perpendicular to each other and also perpendicular to the direction of propagation of the wave energy. So the electric and magnetic fields vibrate in numerous planes at right angles to the direction of propagation of the electromagnetic wave. Although here I only indicated two planes, they oscillate or vibrate in several planes, but they will always remain perpendicular to each other. So polarization is a firm evidence of this transverse nature of electromagnetic waves. Because polarization can occur with electromagnetic waves, then polarization is a firm evidence of this transverse nature of electromagnetic waves. If there are several other planes which are perpendicular to the direction of propagation of energy, then if polarization can occur, then we can know that the oscillations or vibrations initially occurred in more than one plane, or the oscillations were actually perpendicular to the direction of propagation of the wave energy, and therefore this is a firm evidence that electromagnetic waves are transverse. So polarization is a firm evidence to us that electromagnetic waves are transverse. Can we talk about polarization when we are referring to longitudinal waves? The answer is no. Longitudinal waves, such as sound, have their particles vibrate along the direction of propagation of the wave travel, or the particles vibrate parallel to the direction of propagation of the wave energy. So no matter what the orientation of the slit, the waves will be able to get through. Whether the slit is horizontal, the waves will always pass through. After all, the vibrations are always parallel to the direction in which energy propagates. Whether the slit is vertical, the waves will always go through because the vibrations of the waves are always parallel to the direction of propagation of the wave energy. But for transverse waves, the vibrations are perpendicular to the direction of propagation of the energy. So if the vibrations in one plane can be blocked, then we cannot see them propagating through the given slit. So that is the difference between transverse waves and longitudinal waves. We can't talk about polarization when we are referring to longitudinal waves. So longitudinal waves such as sound waves cannot undergo polarization. It's only transverse waves such as electromagnetic waves which can undergo polarization. By the way, all transverse waves can undergo polarization. We have already seen this with the rope, where the rope can be made to vibrate in more than one plane, but these vibrations, when passed through a narrow slit, only vibrations in a specific plane can go through, which means all transverse waves can undergo polarization, although we are going to concentrate on polarization of light. So a light which is unpolarized has vibrations in all planes at right angles to the direction in which the wave is traveling. But when light is passed through a piece of polaroid or a polarizing filter, we call it a polarizing filter. When light passes through a piece of a polaroid or polarizing filter, it is going to become polarized. We can illustrate this with a simple diagram. So the electric and magnetic fields vibrate in several numerous planes as shown by this diagram here. So we can represent unpolarized light by vibrations in several other planes. And then the unpolarized light can be directed into a polaroid or a polarizing filter. Depending on the orientation of the polarizing filter, only vibrations in a specific plane can be allowed to go through. In this case, the polarizing filter is only allowing vibrations in the vertical plane. Therefore, the light is going to be considered to be vertically polarized when it comes through, when it comes out of the polaroid or the polarizing filter. So what has happened? The vibrations of light in more than one plane have been confined into vibrations in only one plane. So we have achieved what we call polarization. So how shall we define polarization? So let's now define polarization. So polarization of light is the process of confining the oscillations of the electric vector in a single plane, normal to the direction of propagation. Now it is normally the electric vector which is confined to be in only as one single plane. Now someone will ask, why not the magnetic vector? So the truth is, when polarization occurs, it is the vibrations or the oscillations of the electric field vector which are confined in a single plane normal to the direction of propagation of the wave. Now the question is, why the electric field vector? Uh, a polaroid consists of a long chain of molecules which are aligned in one particular direction, as we are going to see. The chain of molecules, the molecules in an atom or the molecules in a material cannot absorb the energy of the the energy of the magnetic field. But the electric field, the energy of the electric field or the energy from the oscillating electric field can easily be absorbed by the molecules which make up the material. So, in most cases, the energy due to the magnetic field just goes through a polaroid. It is the energy due to the electric field which is normally absorbed, resulting into what we call plane polarized light. So the process of confining the oscillations of the electric field vector in a single plane, normal to the direction of propagation of the wave, is what we call polarization. Remember, I said an electromagnetic wave comprises of both the electric field vector and the magnetic field vector. These two are always perpendicular to each other, but the magnetic field can easily go through a polaroid. It is the electric field vector whose energy can easily be absorbed by the molecules which make up the polaroid. So that's why we can define it in terms of absorption or confining the oscillations of the electric field vector in only one single plane, which plane is always normal to the direction of propagation of energy. So you can define a plane polarized light waves in an exam as light waves in which the oscillations of the electric field occurs in a single plane. Plane polarized light waves are light waves in which the oscillations of the electric field occur in only one single plane. All the oscillations of the electric field vector in several other numerous planes are cut off, and vibrations of the electric field vector only occur in one plane. So we shall be having what we call plane polarized light. The oscillations of the electric field vector or the oscillations of the electric field occur in only one plane or in a single plane. That's what we mean by polarization of light or plane polarized light. Now you might be asking yourself, how does polarization really occur? Even though it's not a subject of study at this point, I'll just give you a clue about how polarization occurs. So, number one, note that we must have a source of unpolarized light. But plane polarized light can be produced by either selective absorption using what we have called a polaroid. So what we have been discussing here is going to be called a polaroid. There are other methods of polarization which we shall not talk about in details. We have refraction, and so on and so forth. But we shall only talk about selective absorption, where we use what we call a polaroid. So to produce polarized light, unpolarized light is going to be made instant on a plain sheet of a polaroid. The transmitted light will be completely plane polarized depending on the orientation of this polaroid. So the polaroid sheet absorbs the light vibrations in one plane, leaving only vibrations in a perpendicular plane to pass through, as we have seen in our previous animations. So what constitutes this polaroid? I have already mentioned that a polaroid consists of a long chain of molecules. These molecules are aligned in one particular direction and absorb the energy, especially from the electric field vector. The energy from the oscillating electric field is absorbed by these chains of molecules. Any electric field vibrations along these chains of molecules are going to be absorbed. So if the electric field oscillations or vibrations are aligned with the molecules or with the chains of molecules, the energy of the electric field vibrations are absorbed. If the vibrations of the electric field are not aligned with the chains of molecules, then those vibrations just pass through the material. That's when we have plain polarized light. So the energy, of course, which is absorbed, the electric field energy or the energy of the electric field which is absorbed by these molecules is transferred to thermal energy in the polarity. So it becomes thermal energy. So the energy produced or the energy absorbed by the chains of molecules in the polaroid becomes the thermal energy in the polaroid or in the material, rather than being transmitted through the material as the electric field vector to form the unpolarized light. So the electric field vibrations at right angles to the chains of molecules are transmitted with negligible absorption, and those which are aligned or parallel to the chains of molecules are simply absorbed. So if these molecules are arranged vertically, they absorb light waves whose electric field is oscillating up and down. So if the molecules are in the vertical, are aligned vertically, as we are going to see, these if the molecules are aligned vertically, they absorb vibrations of waves whose electric field is oscillating up and down. And if the molecules are aligned horizontally, they would absorb light waves whose electric field is oscillating side to side or in the horizontal plane. So the molecules are arranged vertically. If the molecules are arranged vertically, they absorb light waves whose electric field is oscillating up and down. In other words, the electric field, if the electric field is aligned with the molecules or with the orientation of the molecules, the electric field energy or vibrations are absorbed. Light waves whose electric field is oscillating from side to side then pass through unaffected. This is now what we described as a plane polarized or being plane polarized. I'll give a simple illustration here. So the general rule is that the electromagnetic vibrations that are in a direction parallel to the alignment of the molecules are always absorbed. The general rule is that the electromagnetic vibrations, that is the electric field vector vibrations, which are always parallel to the alignment of the molecules, are always absorbed. This figure below is going to show how the unpolarized light incident at the polaroid is actually going to undergo polarization. So we have the unpolarized light where the vibrations are in more than one plane. If the unpolarized light is incident on a polaroid, in this polaroid they have this long chain of molecules which have been arranged horizontally. So these are wavy blue lines are indicating the arrangement of the chain of molecules. And we have said if the electromagnetic vibrations are in a direction which is parallel to the alignment of the molecules, then they are going to be absorbed. And if it is perpendicular, then they will just pass through. So of course, other angles can easily be reduced. That's why we are just considering the vibrations in a perpendicular plane or perpendicular to the arrangement of the molecules to just go through, because even other angles have components parallel to the components which are parallel to the alignment of these vibrations. That's why we are seeing that only vibrations in the vertical plane are actually going through, and vibrations in all other planes are being absorbed, because all other planes will have components parallel to components in the parallel direction or components parallel to this to the direction of arrangement of these chains of molecules. I want you to note the convention here. By convention, The plane of polarization of electromagnetic wave is defined as the plane in which the electric field oscillates. That's why we said confining the electric field vector into a single plane is what we consider to be polarization. This is by convention, because we believe it is the energy of the electric field vibrations which can be absorbed by the molecules which make up the polaroid. So by convention, the plane of polarization of an electromagnetic wave is defined as the plane in which the electric field oscillates. So the plane of polarization is the one in which the electric field oscillates, or the one in which the electric field can be allowed to oscillate. Okay, so we are still exploring how polarization occurs. Suppose we have more than two polarities. So when two polarities are used, plain polarized light produced by the first polaroid will also pass straight through the second polaroid as shown, since its transmission axis is initially vertical like that of the first one. So if we have two polarities, the first one is going to be called a polarizer, the second one is going to be called an analyzer. So if I have two polarities like this one, the first one will be called a polarizer because it is going to allow only vibrations of the electric field vector in one plane. Then the second one, because the electric field vector was already in one plane, then the second one is no longer a polarizer, it is instead going to be an analyzer. So the analyzer now will only determine the intensity of the electric field vector, which was only oscillating in one plane, that can go through it depending on the angle it is rotated. If I have two polarities, the first one will be called a polarizer, and the second one can no longer be called a polarizer because already the vibrations are in one plane. So the second one normally is called an analyzer. It will now determine how much intensity propagates further in the presence of that second polaroid. Suppose the analyzer is rotated further through an angle maybe greater than, remember they were both parallel, suppose they are not parallel. Let us think of a situation where the analyzer is rotated through 90 degrees so that the transmission axis is horizontal. This time the analyzer will absorb all the light as we are going to see. If we turn the analyzer further through another 90 degrees, now it will have rotated through 180 degrees. Again, the axis of transmissions will be parallel to each other. So this is what exactly I'm talking about. In the first case, we have a polaroid where it makes vibrations of this unpolarized light to only be in one plane as shown here. Then the second polarizer, which we call the analyzer, has been rotated through 90 degrees so that this line here, which is the axis of transmission, which shows the direction in which the electric field should vibrate, it is actually 90 degrees, has been rotated through 90 degrees. It is perpendicular to the first axis of transmission. So because now there is no component of the electric field parallel to the direction of to the transmission axis, then the electric field cannot go through the second polarizer or the analyzer. Therefore, there will be no light transmitted here. There will be no light coming out of here. So the transmission axis of the analyzer is 90 degrees to the transmission axis of the polaroid. And if the transmission axis has been rotated through 90 degrees, then it means there will be no intensity. The intensity of the light coming out from this side is going to be zero. No light is transmitted out because the electric field or the transmitted light from the first polarizer is incident to an axis of transmission which is perpendicular to their direction. Therefore, there will be no transmission. But if we rotate this further through another 90 degrees, now this axis will again be vertical. So we shall see the transmitted light from the first polarizer again emerging here. So whatever happens between 0 and 90 degrees is discussed under what we shall call Malus's law. We know what happens at 90, there will be no light transmitted. But whatever happens between 0, that is if these two were initially parallel, and then now the second one is rotated through 90 degrees. Between 0 and 90 degrees, whatever happens we shall discuss it, or we are going to discuss it under Malus's law. You can always follow these YouTubes to notice to see what I'm talking about under polarization. These videos show animations, or they will show the concepts of polarization using crystals and light being passed through these polarizers, and you see the outcome of polarization. So let's now talk about Malus's law. Let's talk about Malus's law. Remember, we are trying to investigate what happens to the already polarized light between 0 degrees of the second polarizer and 90 degrees. What happens to the polarized light? It's what I want us to discuss here. And this is going to be discussed under Malus's law. Let's think of a situation where initially we have unpolarized light which goes into the first polarizer. All the vibrations parallel the axis of transmission can go through, because the axis of transmission is the direction in which the electric field vector can easily propagate through the polarizer. So let us assume we have only allowed vibrations in one plane. Now we have a second polarizer which was initially, the initial position of the axis of transmission was vertical, but then the second polarizer has been rotated slightly through an angle phi to the horizontal. So we are trying to investigate what happens between, say, 0 and 90 degrees of the between 0 degrees. It means the axis was initially parallel for the analyzer and the polarizer. Then we rotate it through an angle such as phi. So the new direction of propagation is this one here. So this time, not all the vibrations will not be in the vertical. Only vibrations which are parallel to the axis of transmission go through the polarizer. Only vibrations which are parallel to the axis of transmission go through the polarizer, because the axis of transmission shows the plane in which the electric field vector can easily propagate through the polarizer. So it's like a component of this polarized light, which is just parallel to the axis of transmission, will go through. The effect is going to be that the intensity is going to be reduced, because even the amplitude of vibration is going to be reduced, because the component of the vertical in the direction of the plane of the axis of transmission cannot be the same as the vertical component, or cannot be the same as the initial amplitude, if I'm put like that. So when unpolarized light is incident at a polarizer, it is going to be plane polarized. So we have seen a plane polarized light here. The polarized light is now incident on another polaroid, which we call the analyzer, at an angle phi to the axis of transmission. So now the axis of transmission has been rotated through an angle phi from the vertical. So the intensity, like I have said, the intensity of the transmitted light depends on this angle phi. And when phi is 0, of course, when phi is 0, the whole intensity goes through. In other words, when phi is 0, it means the axis of transmission is in the vertical as before. So all the incident intensity here will just go through. So when phi is equal to 0, the plane of incident light is parallel to the axis of transmission. Then the all light will go through the polaroid. And when phi equals to 90 degrees, that is, the plane of the incident light is perpendicular. If now this becomes horizontal, in other words, it will be perpendicular to the first one, because the first one was vertical. If we rotate this through 90 degrees, it becomes horizontal. That is, it is going to be perpendicular. So if the plane of incident light is perpendicular to the axis of transmission, there is no transmitted light. So if we make the plane of transmission to be perpendicular to the incident light, then there will be no transmitted light. In other words, it's equivalent to rotating the polarizer so that the axis of transmission is perpendicular to the incident light. We are trying to explore or to arrive at Malus's law. So let us consider the incident plane polarized light to the polaroid to be of amplitude, I'm going to call it A0. So in this diagram here, the incident light has intensity, which I'm going to call I naught. It has already been polarized to that effect, and it is incident on the second polaroid. And notice that the direction of the incident light is not parallel to the axis of transmission. So it is only a component of this incident light which is parallel to the axis of transmission which will go through. Because the axis of transmission is vertical, so it means whatever goes through must be vertical. This one is not vertical, the incident is not vertical, but is incident at an angle, which angle I've tried to expand here. So it is incident to the vertical at an angle phi. So I've tried to expand it here. So only what is parallel to the axis of transmission, which is going to be a component of this, parallel to the axis of transmission is going to go through. That's why you see what goes through is in the vertical, because the axis of transmission was vertical. So if the incident was this one here, was at an angle phi to the vertical as shown here, the angle here was phi to the vertical, and what should go through is supposed to be in the vertical. Then we are going to need the component of phi in the vertical. We shall need the component of phi in the vertical. We need, the component of the incident amplitude. Let's say this is A naught, which is incident to the polaroid, and what goes out or what goes through is just going to be a component of what is incident onto the polaroid. So I have to resolve A naught to the vertical because only what is parallel to the axis of transmission goes through. So it means the new amplitude, when I resolve this to the vertical, the new amplitude, because the angle is phi, the new amplitude which comes out of the polaroid is going to be A naught cos of phi from your concepts of resolving. So a component of the amplitude transmitted through the polaroid is going to be A naught cos of phi. And remember from our lesson, I don't know which lesson it was, but we know that intensity was directly proportional to amplitude squared. We saw that intensity was directly proportional to amplitude squared. And this therefore means initially, if the intensity is directly proportional to amplitude squared, the incident intensity I naught must have been directly proportional to A naught squared. In other words, I naught before reaching the polaroid must have been equal to a constant times A naught squared. Then after transmission, the intensity transmitted, which I'll just call I, should also be directly proportional to the amplitude. So this will be K times the amplitude which goes through the polaroid, which is going to be I equals to K times A squared. Now the question is, what is the relationship between I and I naught? So if A is A naught cos of phi, so it means I is going to be K. Where there is A, I'll put A naught cos of phi, but this should be squared. And when you simplify it, it becomes K A naught squared cos squared phi. But already we have already said that I naught is equal to K A naught squared. So K A naught squared is the same as I naught. So it's like I is related to I naught by the expression I is equal to I naught cos squared of phi. So thus I naught was K A naught squared, and the intensity transmitted is going to be equal to I equals to K into, where there is A squared, I've put A naught cos phi and I have squared this. When you open that bracket, then you obtain K A naught squared cos squared phi, but already this one here is I naught. Therefore, we conclude that I equals to I naught cos squared phi. So the expression I equals to I naught cos squared of phi is going to be called Malus' law. That expression is called Malus' law. So the relationship I equals to I naught cos squared phi is known as Malus' law, named after Etienne Louis Malus, a French physicist and mathematician. Then the fraction, if I divide I by I naught, the fraction I over I naught is automatically going to be cos squared phi, where of course we know that I is going to be the intensity which has been transmitted through the polaroid. I naught was the intensity which was incident to the polaroid. And phi is the angle between the axis of transmission and the incident light. Phi is going to be the angle between the axis of transmission and the incident light. That is very, very important, and it's what confuses the students many times. So if I was to sketch a graph of I against phi, from this equation here, I is equal to I naught cos squared phi. As a mathematician, you notice that when phi is 0, I is the same as I naught. So that means this is a cosine curve. When phi is 0, I is the same as I naught. When phi is 90, I will be 0. So you can now sketch a graph of I as a graph of I, that is intensity, against the angle phi, or the angle between the axis of transmission and incident light. And at 90 degrees, of course, cos of 90 is 0. So at 90 degrees, we get 0. Then, of course, at 180 degrees, the intensity again becomes maximum. Then at 270, it goes back to 0. At 360, it goes back to maximum, and so on and so forth. So you should be able to sketch a graph of intensity against the angle between the axis of transmission and incident light. This is a very easy graph to sketch. At 90, you just substitute in the formula, I equals to I naught cos squared of phi. When phi equals to 0, I is going to be equal to I naught. That's why the graph starts from here. When phi equals to 90, I is going to be equal to 0. That's why at 90, the graph goes to 0. When phi equals to 180, you get cos of 180 is negative 1, I think, but when you square, I think when you square, you get 1. So because it is squared, it means I is going to be equal to I naught, where I naught is the incident intensity, which is of course the maximum. So you can check and substitute you can check the equation by substituting a few standard angles, and then you sketch the graph of intensity against the angle. So from the graph, there are four. You notice maximum intensity is going to be at 0, 180, and so on and so forth. So 0, 180, 360, 360 plus 1 plus 180, that is 540, and so on and so forth. And we always have zero intensity at 90, 270. So 90, 270, you can predict the next angle there, and so on and so forth. So that is how we deal with polarization on a polaroid. So I showed a simple animation here for people who don't understand what I mean by polarization. So this animation is just showing you how polarization takes place. So initially, we have light with vibrations in more than one plane before reaching the polaroid. And then we have the polaroid, the second polaroid, which is being rotated through several other angles. And you see what really happens when light goes through all these polaroids, or all these polarizing filters. So this animation gives an impression of what really happens when when unpolarized light incident on a polaroid is made to undergo polarization. I don't want to go into the details of all this, but I just want you to notice that as light, which is represented by several unpolarized planes, goes through, it only undergoes polarization if the axis of polarization is parallel to the incident light, or the vibrations are confined to be in only one plane as required by the definition of polarization. Is polarization useful? Then if it wasn't useful, why would we be talking about it at this level? Of course, polarization is useful, even though the uses of polarization are not necessary for this curriculum. I just want to give you a few applications or a few effects where polarization is to be considered. So the following are some effects that use polarization of light. You may research more about them. I will not talk more about them in details. The first one, we have what we call a polaroid glass sunglasses. When light reflects off a shiny surface such as glass, water, or even snow, the reflected light is partly polarized or partially polarized. These reduce glare by one transmitting plane of polarization of light waves only. So the amount of unpolarized light reaching the eyes is reduced. This is how your polaroid sunglasses work. Polarizing filters help in photography, especially to alter the appearance of the sky. So when you look at the sky with polarizing filters, then the appearance of the sky, of course, is going to be altered because the polarizing filters reduce the glare, and this is done by one transmitting plane of polarization of light. So polaroid sunglasses, some of them have what we call polarizing filters or polarides to that effect. Stress analysis in materials. When materials are stressed, for instance, when they form part of a structure such as a bridge, some parts may become more stressed than others. This can lead to unexpected failure for the structure. Engineers make models from transparent plastic materials. If the model is viewed through a polaroid, areas of stress contraction show up where the colored bands are close together. It's the same thing like you pressing onto the screen of your calculator or your computer. Because these have polarides within them, when you press on them, you'll see points where where you have pressed. You have added stress to those points, so they can easily be those points can be easily seen on the screen where you have added some pressure. So the same thing happens when they come up with a model. When engineers come up with a model or come up with a model for a certain structure, they will also make transparent plastic models from transparent plastic materials and try to test them using polarides. And they will view where stress concentrations will always show up before putting the model to the final output, or before executing the model into something which can be utilized in everyday life. Then the other one which I will talk about is the liquid crystal displays, which is found in the laptops and the calculators. The liquid crystal displays of some calculators and laptop screens produce a plain polarized light. You can investigate this effect by putting a piece of polaroid over the display and rotating it. Or you can twist the polaroid on your calculator display and see it vanish. So you can try to press on your computer, or you can try to press on your calculator screen and see what really happens. It's only because the liquid crystal displays have polarides on them. So it means polarization could have some applications, but like I say, these applications are not necessary for the AS curriculum. Self-check. Set what is meant by plain polarized light, so that one I've mentioned, confining the electric field vector into one plane, confining the electric field vector of light into one plane, or making the oscillations or vibrations of the electric field into one plane. Vertically plane polarized light is incident on three polarizing filters. There are three. The transmission axis of the first polaroid is vertical. Okay. The transmission axis of the second filter is 45 degrees to the vertical, and the transmission axis of the last filter is horizontal. Determine the intensity of light emerging from the final filter. So without calculation, the final intensity is 0, because if the first one is vertical and the final is horizontal, so this angle is going to be 90 degrees, so the final is going to be 0. In other words, using I equals to I naught cos squared theta or cos squared phi. So I is going to be equal to I naught cos squared of 90. So from the final, it is going to be 0. Plain polarized light of intensity 20 watts. Alternatively, by the way, you could first find the intensity which comes from the incident intensity, let it be I. The intensity which comes from the first filter is going to be I1 is going to be equal to I cos, because I is what is incident on the second filter, that is I cos squared of 45. Then now this is going to be incident on the third filter, so the next one is going to be I2, which will be equal to I1 cos. Because it is horizontal, it has been moved through a further 45, so cos squared of 45 again. So this means this is going to be I2 equaling to I cos squared 45 for the first one, then cos squared of 45. I don't think this was not true, because they said the transmission axis of the second filter is 45 to the vertical, and the transmission axis of the last filter is horizontal. That means what is coming from the second filter is what is incident on the last filter. So I think this was not correct. No, the fine is not 0. So this is going to be, for the first one, I think this is 0. This is a half of I. Then for the second one, this is going to be a half of I times a half, which becomes a quarter of I. So this is going to be I divided by 4. It's not going to be 0. Unless, because remember, the light was vertically plane polarized and it was incident on the first one, it went through as I. Then the second one, the angle of rotation was 45 degrees. So it means what leaves the second one is not perpendicular, is not vertical, because theta is the angle between the axis of transmission and the incident. So the incident from the second one is not perpendicular to the transmission axis of the final, because it came out from an angle of 45 degrees. So it is going to be a quarter. It is going to be a quarter of I, where I is the incident, or it is going to be a quarter of I naught if I naught is the incident. Maybe I can repeat this systematically. So let's say this is the first one, and we say this is the second one, and we have the third one. So what comes from here, from the first filter, is say vertical. Light is incident vertically here. And let's say this is the second filter. What comes from this is in this direction. And this is the third filter. So what comes from this must be horizontal, must be like this. So for the first one, let's say the intensity which comes from the first one is I naught, and it reaches on this one. Let's say this is I1, and what comes out from the one which is horizontal is I2. So to find I1, I will say I1, because I naught is the one which is incident on the second one. So I1 is going to be equal to I naught cos squared of 45, which is the same as I naught divided by 2. And then I naught divided by 2 is incident on the third one. So I2 is going to be equal to I1 cos of, again, because to reach horizontal, it is moved to 45 in comparison to the second one. So it is going to be cos squared again 45. So this is going to be equal to I naught over 2 times cos squared of 45 again is a half, which gives us I naught divided by 4. So I think here the answer is going to be I naught divided by 4. Plain polarized light of intensity 20 watts per meter squared is incident at a polaroid. Calculate the intensity of the transmitted light when the angle between the plane of polarization of the incident light and the transmission axis of the polaroid is 30. So remember, the formula is very simple. I equals to I naught cos squared of theta, or cos squared of phi. Because here we are considering these angles independently. If phi is 30, cos of 30, I naught is 20, so I'm just substituting this formula in my calculator. You can also verify. I'll just substitute for only 2. Cos of 30 squared times 20. So here the answer is 15 watts per meter squared. Of course, here the answer is 0, because cos of 90 is 0. You can check the rest using the same formula. Plane polarized light is incident at a polaroid. Calculate the angle theta, which gives transmitted light of intensity 60% that of the incident. So if the incident is I naught, what is transmitted must be 60%. Intensity transmitted is equal to 60% of I naught, which is going to be 0.6 I naught. That is what is transmitted. So from I equals to I naught, cos squared of theta. So it means cos theta is going to be the square root of I, which I is 0.6 I naught divided by I naught. I just made cos theta the subject. So this means the theta is going to be equal to the square root of 0.6 is root of 0.6. Then I get the sine, the cos inverse. Theta is going to be the cos inverse. Let me write it here. Cos inverse of root of 0.6, which is which is 39 degrees. Yeah, I think polarization should stop here. See you in lesson 8. This is the last part of waves. The next part is going to be lesson 8 is going to be superposition. Until next time, bye bye.